Okay, so this is section 4.1, inverse trig functions. And here's where we, talk about inverse trig functions. So if you haven't, you probably want to look at the Math 92 lecture for this week, because that's where we talk about the kind of foundation of what we're going to do right now. Okay, so we have our trig functions. So in this section, we're going to talk about the inverse trig functions of sine of x, of cosine of x, and of tangent of x. You can do all the others as well, but they're rarely used, almost never used. And so we're only going to focus on the three kind of main trig functions. If you do want to think about the inverse functions for the other guys, it's a good exercise to try to figure out, how they would work as well. All right, but it is exactly the same idea. Okay, so let's start with sine of x. So we know sine of x, the graph of it is, so let me write f of x equals sine of x. We know the graph of it looks like this, right? And it oscillates like that, continues on forever. Let me label a couple important points here. That one here is pi, that one here is pi over 2, that one here is minus pi over 2, that one here is minus pi, and of course one period is 2 pi here, and then this guy here is minus 2 pi. Okay, those are the relevant ones for this discussion here, or some of these are relevant. Okay, already we see that sine has no inverse because it doesn't satisfy the horizontal line test. Every horizontal line, or many horizontal lines, are actually going to intersect the graph at an infinite number of positions, right? Infinite number of places. And so the horizontal line test does not work. Okay, and so it has no, this function, as I'm looking at it right now, has no inverse. So we do what we talked about in Math 92, we throw away part of our function, and we want to throw away exactly enough so that it has an inverse, but we don't want to throw away too much, right? So if we look at this graph, kind of what we did with the parabola in Math 92, we can see that if I, oops, sorry, that's the eraser. If I keep this part here, this shaded region, then what's left is actually going to satisfy the, that's terrible. What's left is going to satisfy the vertical line test, right? Because if I throw everything else away when I do a horizontal line, right, it only touches at one place. Okay, so let me draw that portion just by itself right here. So, this one. So if I just draw it by itself, I'm going from minus pi over 2 to pi over 2, right? So that would be from here to here, right? And the graph looks like at here is minus 1, there's 1. Our graph looks like that. Okay, so we're throwing away the parts that are past here and past here. Okay. All right. So now if you take a look at this second graph here, that definitely satisfies the horizontal line test. So this guy here definitely has an inverse. And that's what we mean, the inverse of this guy, the kind of fixed or kind of chopped up sine x. That's the one that we refer to when we say the inverse of sine. Okay. Okay, before we actually draw anything or write anything further, let me say that I chose this boxed region to keep and throw away everything else because it's the most natural region in a way. If you think about the graph of sine, let me do it here. If you think about the graph of sine, right? Alternatively, what else could I have done? I can't keep, for example, let me shade it in again. I can't keep this region here, let's say, from 0 to pi, because it would touch, horizontal lines would touch at two places, right? So kind of, and we always want things to be near 0, right? We don't want to kind of work with the portion of sine that's far away from 0 if we can avoid it, because 0 is a nice number, right? Sine of 0 is 0. So because sine has this kind of nice relationship with 0, we want to keep the portion that's near 0, around 0. And the best portion of it is exactly the one that I've chosen. Okay. Alternatively, I could have chosen, just like we talked about with the x squared function, we could have chosen to keep different parts of the x squared function. I could just as easily have chosen to keep, let's say, this part of the sine function, right? So the part that goes from here, oops, in terms of the picture, the part that goes from here to here, right? And that would have a legitimate inverse as well. But it's kind of far away from kind of the interesting zero, sine of 0 equals 0. Okay. All right, so there's always, when you're throwing away parts of a function, there's always some sort of arbitrariness in terms of which parts I decide to keep. All right, so regardless, by convention, when we talk about the inverse of the sine function, we are throwing away everything except this portion right here. Okay. All right, so what is this function? Let me call it capital F, just in line with how I did it in Math 92. But I'm only looking at x between minus pi over 2 and pi over 2. All right. So this is analogous to the parts where we said we only look at x bigger than 0 for the parabola. Okay, so this guy has an inverse. This has inverse, right? And we call the inverse, the inverse arcsine of x. All right, so that's the name. That's the name that we give the inverse, arcsine. So this is an ARC. Okay, an alternate way to write it is sine to the minus 1x. All right, so this is kind of inspired by the notation of f inverse, right, with the being denoted by the -1. Okay, but again, the f to the -1 doesn't mean we're taking it to the -1 power, or this notation doesn't mean we're taking it to the -1 power. And so this sine to the -1 is not to the -1 power. All right, it means inverse. Okay, so if you did want to express sine to the -1 power, you should probably write it like this. All right, or just write it as 1 over sine x. Okay, or I guess you could write it as cosecant x. Right? But never ever put the -1 there because that means arcsine. That means the inverse of the sine function. All right. Let's look at a picture. So if we want to draw the picture of the arcsine, we would flip the picture we have above across y equals x. It's really hard to draw it in the same picture here because of the curves of sine. So I'm going to draw it in a separate picture. Let me note down some interesting points in the picture above. So this point up here has coordinates pi over 2 comma 1. This point down here has coordinates minus pi over 2 comma minus 1. And this point, of course, is 0 comma 0. All right, I want to write them down because I know when I look at the inverse function, I'm going to pass through the points where these guys have swapped coordinates, right? So my original function goes through pi over 2 comma 1. So my inverse function is going to go through 1 comma pi over 2. All right, so 1 here, pi over 2 there. So my inverse function passes through that point right there. Okay, because again, this pi over 2 represents x. This 1 represents y. And in the inverse function, right, the x's and the y's are swapped. And so I have 1 comma pi over 2 as opposed to pi over 2 comma 1. Okay, now the same thing for the other points. At 0 comma 0, we swap 0 and 0, we still get 0, 0. So we have to go through the same origin, of course, the origin, of course. And then the last point was minus pi over 2 comma minus 1. That becomes minus 1 comma minus pi over 2. So right there. All right. So our graph, we know, has to pass through these 3 points. Let me look at another interesting feature here. Let me use a different color. Sine at pi over 2, this guy is at the very tip of top at pi of sine, right? It's at the highest point. So it just touches that horizontal line like this. And at the bottom, it just touches the horizontal line like that. All right. When I flip y equals x, those horizontal lines become vertical lines like this. Okay. So I know that my arc sine has to just touch this vertical line and just touch that vertical line. And so this really helps me draw the arc sine. It looks like this, like that, and like that. Okay. All right, so this is arc sine of f of x equals arc sine of x. Okay, couple things to note. Look at my domain. Domain is minus 1 to 1, right? And that, of course, is the range of my original function because x and y's are swapped. So domains and range are swapped, all right? So what this means in particular is you're never allowed to plug in a number bigger than 1 into arcsine or a number less than 1 into arcsine, right? And that also makes sense because sine itself can never be bigger than 1. Sine itself can never be less than minus 1. All right. So that's our picture. Let's write down a few values for arcsine. So arcsine of, let's say, 1, right? What is that? So that's going to be pi over 2. And we can, for that one, we can see exactly on the graph what it is. All right? Okay. So one thing to note, the output of, I should write this down. So output is angle, or is an angle. Okay, so the output of an arcsine is an angle because the input and the outputs are swapped between sine and arcsine, right? Sine, you put in an angle and you get out a number. So arcsine, the way you should think of it is you put in a number and you get out an angle. All right, so very frequently you'll want to have this interpretation of the output of arcsine. Not always, but very frequently. All right, so that, again, the output of arcsine, very frequently you want to think of it as an angle. So in goes a number, out comes an angle. Okay, arcsine, and another one we can just see from the picture is arcsine of minus 1 is equal to minus pi over 2. Another one we can see from the picture is arcsine of 0 equals 0. But let's do some kind of more interesting ones. Arcsine, and let me now use the alternate notation, just so we can get used to using all the different kinds of notation. 1/2. So what is this? And again, inverse function is you're swapping the input and the output, right? So this is, let me write it like this. Asks sine of what is equal to 1/2. All right. Or let me do it like this. This equals question mark is equivalent to sine of question mark equals 1/2, right? I kind of like this because here you can see the output and the inputs are swapped when you compare arcsine and sine. And then here, input and outputs are swapped when you compare, again, arcsine and sine. Okay? So whenever, we're not used to working with arcsines. So if you are asked to calculate arcsine of something like 1/2, I think it's very useful to convert it into an equivalent question about sine. All right. So arcsine of 1/2 is equal to what? Is the same as sine of what is equal to 1/2. All right. And this one we're more familiar with because we've worked with sines a lot, right? And hopefully we've memorized at this point that when you plug in pi over 6 into sine, you get the output 1/2, right? So this guy should be pi over 6. And so what that means is that arc sine of 1/2 should be pi over 6. Okay, and here we have to be a little careful because actually there's potentially many inputs we can put into sine to get the output 1/2. But what we're doing here is we're looking at sine only between minus pi over 2 and pi over 2, right? So even though there's many answers, potential answers to that question, sine of what is equal to 1/2, we only want the answer that's between minus pi over 2 and pi over 2. Okay, so the pi over 6 is between minus pi over 2 and pi over 2, so we're all set. Okay, so of course, the ones we've kind of memorized, it's all cool, right? We've memorized them all as being between the correct angles. What I mean by this is, what's arc sine of root 2 over 2? That's equal, let me write it like this, equals to what? That's equivalent to sine of what is equal to root 2 over 2. And again, this one we've memorized, that should be pi over 4, all right? And so arc sine of root 2 over 2 should be pi over 4. And again, pi over 4 is between pi over 2 and minus pi over 2, so we're all set. Okay. All right, one more. Arc sine of, let's say, root 3 over 2 equals what, right? What is this? This is the same as sine of what is equal to root 3 over 2. And again, we've memorized this. Sine of pi over 3 is root 3 over 2. And so arc sine of root 3 over 2 should be pi over 3. And again, pi over 3 is indeed between minus pi over 2 and pi over 2. So we're okay. All right. And again, we're pretty much always going to be okay for these kind of memorized values because that's how we've memorized them as angles that are, relatively small angles. 30 degrees, 45 degrees, 60 degrees are all less than pi over 2, which is 90 degrees. Okay. Of course, since we're talking about the inverse here, we have the usual fact that sine inverse of anything, root 3 over 2, for example, this should be equal to root 3 over 2, right? Because when you're doing a function after its inverse, right, then you should just end up with whatever you put in, right? Your output should be whatever you put in. And again, people colloquially say this as, sine and arc sine cancel each other. All right. Okay, it works this way fine, but you have to be a little careful the other way. Arc sine of, let's say, 4 pi over 3. All right. So normally, if everything were kosher with the function that we're working with, in that it has an inverse, then this would just be 4 pi over 3, right? But remember that sine, we had to do some manipulation. We had to fix it. And so in our fixing, we had to throw away parts of it, right? And so here, we can't just say it's 4 pi over 3 because actually 4 pi over 3 wouldn't even be in the range of arc sine, right? Arc sine is always between minus pi over 2 and pi over 2, right? And so this one you can't just blindly say is 4 pi over 3, all right? So that's not going to be correct. So one way to think through this is, well, there's a couple ways to do this. The most kind of brutal way is just to calculate sine of 4 pi over 3, right? Sine of 4 pi over 3. Let's do this. I'm going to draw the graph, right? 4 pi over 3, that's bigger than pi, right? Because pi is 3 pi over 3. 4 pi over 3 would be here, right? And the distance between pi and 4 pi over 3, pi is, let me again emphasize, pi is 3 pi over 3, right? And so this gap right there is pi over 3. Okay? All right. That's really important because the way I'm going to figure out sine of 4 pi over 3 here is I recognize that if 4 pi over 3 is here, that value there, right, is going to be the same as that value there, except negative, okay, because of the symmetries of these humps, right? So this hump right there is in a way symmetric to that hump right there. All right. So in other words, if this gap right here is pi over 3, then that value up here is the same as that value there, except with negative becomes positive, or positive becomes negative also. All right. But we know sine of pi over 3, right? Sine pi over 3 is equal to root 3 over 3, right? And so this is the same as saying arc sine of root 3 over, root 3 over 2, negative of root 3 over 2. Okay, oops, that looks, can't see that, so let me write it like this, root 3 over 2. Right, negative because sine of pi over 3 is positive root 3 over 2, and what we're looking at is negative of that. Okay. All right, and where is that? Sine of what is minus root 3 over 2? Well, if we look in this picture here, right there, right? Where this gap here is again pi over 3. Okay, so this tells me it should be minus pi over 3. All right. Okay, another way to kind of reason this out is to look at this 4 pi over 3. And this is a little more direct, but perhaps we're not as used to kind of working with angles that are negative. But this 4 pi over 3 is right there, and that's symmetric to that hump right there, the negative side of the hump. And so since this gap here is pi over 3, then that gap there has to be pi over 3. And so we know that sine of 4 pi over 3 is the same as sine of negative pi over 3, right? And so in that way, arc sine of 4 pi over 3, we've reasoned that that's now the same as arc sine of pi over 3, right? Sorry, of root 3 over 2. Sorry, 4 pi over 3. Somehow I confused myself a little bit there. Sorry, is equal to sine of negative pi over 3, right? And because this minus pi over 3 is between minus pi over 2 and pi over 2, I can just write that immediately. All right. Okay, so it's just something to be a little bit careful about when you're computing arc sine after sine. Okay, this argument here about the symmetries, we'll talk about this in more detail in our next section. It'll be very important for us in the next section. So if you're not completely used to it at this point, the next lecture will go into it again. Okay, let's do cosine. So the question is, what is the inverse of the cosine function? Well, again, there's a problem. Cosine function has no inverse because it doesn't satisfy the horizontal line test. So we have to toss or throw away parts of the cosine function. And traditionally, what we do is we throw away, we throw away everything outside this shaded area here. All right, so this would be between 0 and, between 0 and, I did it again, between 0 and pi. All right, why this portion? Again, it's kind of arbitrary, but we like to choose this portion because it includes 0, right? And if we are going to include 0, this is the most natural region to choose. Okay, we certainly cannot choose anything to the left of 0 and things to the right of 0, because that would mean that we wouldn't satisfy the horizontal line test. So it has to be only stuff to the right of 0. All right, and we can only go up to pi, because if we include any more than pi, if we include anything more than pi, we're not going to satisfy the horizontal line test down here. Right, so this is the biggest region that we can kind of keep. So instead of looking at the function here, this is, again, f of x equal cos x, we look at the kind of fixed version or truncated version or chopped up version only from here to here. All right. Okay, and again, this here is -1, this here is 1, and so that point there has coordinates 0, 1, because I'm gonna draw it in 1 second. So I want to know the coordinates. Sorry, I'm going to draw the inverse in 1 second. So I want to know the coordinates of all these interesting points. So this is pi over 2 comma 0. Okay, so what's f inverse? So let me emphasize here, x is only between 0 and pi. Okay, so f inverse of x is legitimate, and it looks like, let's see. So this point here is 0, 1, right? So in the inverse function, I have to swap the coordinates. So that's going to be 1, 0. All right. This point here in the middle is pi over 2, 0. So that's actually 0, pi over 2. And then this point here is at a height pi, is pi comma -1. So it should be at -1 comma pi in my inverse. All right. For my cosine function, I'm kind of just touching this horizontal line and just touching that horizontal line. So for the arc cosine, I should just touch that vertical line and just touch that vertical line. Okay. And so this leads me to this picture here. All right. Same idea. And again, notice that my domain is -1 to 1. All right. I can only put in points between -1 and 1. And again, that makes sense because cosine is never, the output of cosine is never bigger than 1. So the input of arc cosine can never be bigger than 1 because, again, inputs and outputs are swapped. Okay, so I'm going to do this discussion a little faster because everything kind of mimics what we talked about with sine, except now it's cosine, right? And now we've had to choose a different portion of the graph, but the ideas behind everything is still the same. So for example, so first of all, notation, arc cosine would be our notation, or cosine inverse x is our notation, all right? And of course, in terms of values, right, arc cosine of, let's say, so sorry, let me just do an easy one here, of 0 is pi over 2, right? Arc cosine of, let's say 1/2, right, is equal to what? Well, if we're not sure, we think about this as cosine of what is equal to 1/2, right? Cosine of, hopefully, again, we've memorized this, pi over 3 is 1/2. And so therefore, arc cos of 1/2 is pi over 3. Okay. And so on. And again, our right-hand sides for arc cosine, just like with arc sine, we frequently want to think of this guy as an angle. All right. Okay. And again, our because we've thrown away parts of our function, we have to be a little careful when we work with arc cosines, right? So, for example, arc cosine of 3 pi over 2, right? We have a inverse function, right? A function followed by an inverse function. Normally, that should be 3 pi over 2, but it's not because of the fact that we had to throw away parts of cosine, right? And so what is it actually? Well, we can look at the picture of cosine again. 3 pi over 2 is right there, right? We want to look at, when we're thinking about our cosine function, we want to look at the equivalent kind of point that's between 0 and pi, right? And so that would be this one, okay? Cosine of 3 pi over 2 is the same as cosine of that guy, right, which is pi over 2, okay, which is 0. And so this is actually going to be pi over 2. All right. All right, again, you can just, if you just want to brutally compute, you can just brutally compute, right? Cosine 3 pi over 2, because of the picture, that's 0, equals arc cosine of 0. And then now you just think cosine of what is 0? And that what has to be between 0 and pi. And so again, you get pi over 2. Okay, so that's just a small thing that we have to be a little careful about. Okay, finally, tangent. So tangent, luckily for us, tangent is very straightforward. Tangent looks like this with asymptotes. Let me do the asymptotes in a different color. With asymptotes here and here, and then it just repeats. Right, repeats every pi as a period of pi. The coordinates of these asymptotes, pi over 2, minus pi over 2. Remember, it's going to be exactly where cosine is 0. And of course, the asymptotes repeat as well. So this one would be at minus 3 pi over 2. This one would be at 3 pi over 2. Wrong color, but it's okay. 3 pi over 2. Right? This one is at 0, so that one is at pi. That one is at minus pi. All right, because again, it repeats every pi. So this distance here is pi. Okay, so for tangent, again, technically, it does not have an inverse because it doesn't satisfy the horizontal line test, right? We have inputs, we have outputs that correspond to many inputs. So we have to toss part of it. And here, this is kind of simpler because it's very natural which parts to toss, right? Or which parts to keep. It's pretty obvious that, we would like to keep this part. This is kind of the most simple region to keep. Okay, so for tangent, we keep the parts that's between minus pi over 2 and pi over 2. All right. And in that way, if we only keep that part, right? So if this is f of x equals tangent x, our kind of fixed function, or the function where we've chopped it up, is only going to be this part here. And this guy satisfies the horizontal line test. So this guy has an inverse. So everything here is legal. And it looks like, so this is a really interesting function because it's a function that has horizontal asymptotes. And the horizontal asymptotes are actually different, right? This one has an asymptote at pi over 2. And this one back here on the other side is at minus pi over 2. All right. Okay, one nice thing about arctangent, so this would be arctangent. So same notation, of course. And we also use tangent to the minus 1x as well. The very nice thing about arctangent is that you don't have to worry about its domain because its domain is everything. All right. Okay, and again, if you're asked to compute, what's arctangent of 1, let's say, right? That's the same as asking tangent of what is equal to 1. And again, that what has to be in this shaded region up here. So it has to be between minus pi over 2 and pi over 2. All right? So what has to be between pi over 2 minus pi over 2? Okay. But luckily enough for us, we usually have memorized the values that are actually between those two guys. And so this what is going to be pi over 4. Okay? Because sine pi over 4 is the same as cosine pi over 4. And so tangent pi over 4 should be 1. Okay, and so arctangent of 1 should be pi over 4. And again, it should be frequently it should be thought of as an angle. All right, so this is our introduction to the inverse trig functions. If you use your calculator to calculate inverse trig functions, it's exactly the ones that we've talked about here, right? So if you input any number into your calculator for arcsine of 0.072, its output is going to be between minus pi over 2 and pi over 2, just as we said, all right? So everybody, by convention, uses the same kind of fixing function and throws away the same parts by convention. Okay, so finally, let me do one more thing. And this is a nice way to shortcut some computations. And also, it's a nice way to allow us to rewrite some expressions in a very nice way. So what I mean by this is, let's say I'm asked to compute cosine of arctangent of x. All right. Okay. So normally this would be kind of a hard thing to deal with because, first of all, we have trig function. Second of all, we have a inverse trig function. And third of all, we're kind of combining a trig function and an inverse trig function in a composition. So very hard to work with this. But if we look at this in the right way, we can actually rewrite this very nicely. And you'll use this in calculus if you are going to be taking calculus in the future. So how do we want to think of this? So I've emphasized all throughout this video here that the outputs of the inverse functions, you frequently want to think of them as angles. So I want to think of this guy as an angle. All right. So I'm going to name this angle theta. All right. And what is the interpretation of this theta? Well, as we said, arctangent asks the question, arctangent x, right, being equal to theta is the same as tangent of theta equals x, right, where I'm swapping the input and the output. Swapping the input and the output. That's moved me from arctangent to tangent. All right. So this, if I name this inside of the cosine, this arctangent x equals theta, then I have that results in the formula tangent theta equals x. All right. Now this might feel bad because I've introduced yet another kind of quantity, theta, here that wasn't there before. But what's really nice is now I can draw a picture, right? So let me draw a right triangle. Theta here, right triangle, right? What's tangent theta? Tangent theta is opposite over adjacent, right? So opposite over adjacent should be equal to x. Now, if I can think of x as x over 1, and so if I draw a right triangle with opposite being x and adjacent being 1, then this triangle, tangent of this theta right there, is going to be x. All right? So for this right triangle, in a way, it represents this formula right there. Okay? All right, so this is a really neat trick because what am I asked to compute? I'm asked to compute cosine of theta, essentially, right? What's cosine of theta? Now that I have this right triangle, cosine of theta comes very easily. Cosine theta is adjacent over hypotenuse. What's the hypotenuse? Well, I have the Pythagorean theorem. The hypotenuse is square root 1 plus x squared. Okay, and so cosine of theta, which is exactly what we want, right? is equal to adjacent over hypotenuse. And so altogether, so ultimately cosine of arctangent of x is 1 over square root 1 plus x squared. So what, potentially looked really, really ugly is, decently simple. Or what's really interesting is there isn't even a trig function here on the right-hand side. All right. Okay, so you can do this with all combinations of the trig functions, right? So if I wanted to, for example, compute, let's say, tangent of arc cosine of x, right? I could do the same idea. Tangent of arc cosine of x. Again, arc cosine is to be thought of often as an angle. Let me call that angle theta, right? If I call that theta, then what I'm saying is arc cosine x is equal to theta. And that's the same as saying cosine of theta is equal to x. And then I can draw a triangle representing that fact. Theta here, right triangle, adjacent is x, hypotenuse is 1, right? So I'm thinking of x as x over 1. So adjacent is x, hypotenuse is 1. That means this opposite side has to be square root 1 minus x squared, all right? And so tangent of arc cosine of x is equal to tangent of theta. And from my picture, I can see tangent of theta is opposite over adjacent. So I have a very nice formula for, again, something that looks potentially kind of ugly. All right, so you'll see a bunch of these on the homework, and you'll see this probably around second semester calculus or second quarter calculus if you're in a quarter system. One thing to note about this that I'm not going to dwell on and I won't trick you with, but you do actually technically have to be a little careful with doing these because the way I've drawn these, right, I'm actually drawing a triangle. And I'm drawing a triangle with side length up here, right? Side length is x. And down here, side length is x. But what if x were negative, right? Then I would have some issues here. So I've glossed over that for this discussion. I'm not going to trick you about, with this in our exams or anything like that. Just do the problem as if everything were cool and the triangles were all legal. Don't worry about it. All right. Even in calculus, when you see it, you probably won't need to worry about it. But just keep in the very, very back of your mind, be aware that technically we have to actually be a little careful. If the input x were negative, we have to modify this idea here a little bit. For example, instead of writing this side as x, it would be negative x, right? Instead of writing this side x down here, it would have to be negative x. And we would actually have to pop out a negative sign here. Okay, so in that situation, this formula over here would have to be split into two different formulas depending on whether x is positive or negative. But again, let's not worry about it. Let's pretend drawing this triangle always works. Let's pretend our inputs are always positive. All right. Okay, in any case, the last little note is I've done this with kind of a very in a very general way. That gives us a general formula. But you can do this with numbers as well. So if I ask you sine of arctangent of, let's say 5/4, right? I can, again, think of this guy here as theta. And so I'm saying arctangent of theta is 5/4. And so tangent of theta, arctangent of 5/4 is theta. And so tangent of theta is 5/4. I can draw a triangle representing this fact. Tangent is opposite over adjacent, 5/4. And so that means the hypotenuse is 4 squared plus 5 squared, which is 16 plus 25, which is 39, right? And so we end up with this is equal to sine of theta. And then again, referring to our triangle, sine of theta is opposite over hypotenuse, 5/39. So we can calculate this really, really easily without having to think too hard about the actual values of sines and arctangents in this problem. Okay, so this is a very neat trick. And again, in calculus, the actual formulas for these functions are really important. The last note is, notice I have arctangent of 5 over 4. 5 over 4 is bigger than 1, but that's perfectly legal because arctangent can take inputs that are bigger than 1. Because arctangent, again, let me draw the picture. Arctangent looks like that, right? So it has inputs. It's allowed to take inputs of any value. Right? If I had written arc sine of 5/4, that would actually be illegal. All right.